Hello, everyone. So today we're going to talk about integration. Integration is an absolutely massive topic, and it's almost infinitely complex. It has infinite complexity. I don't know if I've shown you a meme. Yeah. So this was the diagram showing the difference between finding the derivatives and integrating, and we are just barely going to touch integration, just the very basics, the tip of the iceberg. But I'm sure most of you will go on to doing some very interesting integration in your life. So yeah, so integration. So integration is basically the anti-differentiation. It's the opposite of finding the derivative. So, for example, we know that the derivative of x squared is 2x. It means that the integral of 2x is x squared. Simple as that. Well, sort of. We write dx here. Dx is just the the uh, well, the variable. You indicate the variable you're integrating by. So for you, for now, is just a technical thing. You always write integral of 2x x squared. So it's the integral of 2x, which is integral of 2x dx. Anyways, but x squared is not the only function that has the derivative of 2x. It has, uh, so for example, x squared plus 3 is also 2x. And x squared plus 5 is also 2x. So actually, it's not just x squared, it's x squared plus c, where c is any number. We call it the integration constant. So when you're finding the integral, you're trying to find a function whose derivative is that, and it always contains c. Okay, let's do the integral of let's do an integral of 3x squared dx. Well, we know a function whose derivative is 3x squared. It's x cubed. X cubed plus c, as simple as that. So we will use three standard results. I'm giving them without proof, three standard results. Well, sort of without standard results. And they are as follows. The integral of a constant, well, of a k dx, where k is a constant, is just kx plus c. The integral of, so not 3 is going to be more standard results. X to the power n, the integral of x to the power n is x to the power n plus 1 divided by n plus 1 plus c. It is important to note that n is not equal to -1, because if n does equal to -1, then you're dividing by 0. So this formula does not work for n equals negative. And the integral of cosine x is sine x plus c, because you know that the derivative of sine x is cosine x. And the integral of sine x is minus cosine x, because you know that you know that cosine derivative of cosine is minus sine, so the integral of sine is minus cos. Okay. Hope that makes sense. Any questions here? Another question. Did you learn something new just now, or yes or no? Did you learn something new? Yes or no? In the chat, please. So about 50-50. Oh, actually, more people saying yes. Good. Lovely. Okay, so integral is linear. It's a very important, it's a massively important property. What does it mean that the integral is linear? Linear means that the integral of f plus g is the integral of f plus integral of g. I'm missing the dx here, but obviously I mean dx, dx, and dx. Right. And also, so linearity. That's the first property. And the second property of the linearity, if you have a constant multiplied by f dx, is k integral f dx. So you can take out a constant out of the integral, and we will use that a lot. And secondly, the integral of a sum is the sum of integrals. So let's use this property here. So using linearity, we can write it's the integral of 3x to the power 4 dx minus integral of 5x squared dx plus integral of 7 dx. And I'm going to take out the 3 here. So it's 3 integral of x to the power 4 dx minus 5 integral x squared dx plus, well, we kind of, okay, let's keep it 7 integral of 1 dx. Okay. So using the second formula, x to the power n, we know it's x to the power n plus 1 divided by n plus 1. So it's going to be 3 multiplied by x to the power 4 plus 1 divided by 4 plus 1 minus 5 multiplied using the same formula, x to the power 2 plus 1 divided by 2 plus 1 plus 7 I forgot C. So technically, I have to write C everywhere. So plus C1 because plus C2 plus integral of 1 is x. So 7x plus C3. So what I get, because the integral of 1 is x, right? So that's going to be 3/5 x to the power 5 minus 5/3 x cubed plus 7x and then plus C1 plus C2 plus C3. We're going to take C1 plus C2 plus C3 and we're just going to replace C is C1 plus C2 plus C3. And for that reason, you don't have to, you can just write plus C. You don't have to write C1 plus C2 plus C3. You don't need 3 constants. You combine them into 1. And that's it. And that's the solution. Let's check. And let's use a different color to check. Let's take 3/5 x to the power 5 minus 5/3 x cubed plus 7x plus c. And we find the derivative of that. And it's going to be 3/5 multiplied by 5x to the power 4 minus 5/3 3x squared plus 7 plus 0, which can be simplified to 3x to the power 4 minus 5x squared plus 7. And that's it. That's exactly what we have. Lovely. Okay. Now, this function, the primitive function, primitive function, or also known as the antiderivative. Derivative. So if f dash of x is equal to f of x, then f of x is the antiderivative of f. That's the definition. Example. If f is if f is 4x cubed, then f of x is x to the power 4. Kind of makes sense, hopefully. So the integral of f of x dx can be written as f of x plus c. That's the rule. Okay, so that's the antiderivative. Derivative, or the primitive function, also known as the primitive function. If you have a definite integral, then the integral between limits, that means you have limits from a to b of f of x dx, is the primitive function at point b minus the primitive function at a. And that's called Newton. I forgot. Newton-Leibniz formula. Yes, Newton-Leibniz formula. Yes, Newton-Leibniz formula. Is it? Yes, of course. Fundamental theory of calculus. Lovely. So how does that work? Well, you find the antiderivative of the function. You find the function you have a function whose derivative is f of x, and then you substitute b and a, and then you subtract and you get a number. So a definite integral is a number, and that's very important. So this is what a definite integral looks like. It has numbers here. And so what we need to do is we find the integral. So we use the formula. So 2x to the power 4 divided by 4. Yes, so we're using that formula. X to the power n dx is x to the power n plus 1 over n plus 1 plus c. And then you have, okay, minus x squared over 2. And then you draw rectangular brackets or square brackets, and you put 1 and 3. And then what you do is you substitute 3 into. So 2 and 4, that simplifies to 2. So there's going to be 3 to the power 4 over 2 minus 3 to the power 2 over 2 minus, and you subtract. So this is f of 3 and minus f of 1. So that's 3 to the power 1 over 2 minus 3. Sorry, 3 to the. What am I doing? Sorry. 1 to the power 4 over 2 minus 1 to the power 2 over 2. Okay. Well, that's 0. So it's 1/2 minus 1/2. So that's 0. That's fine. So this is 3 to the power 4 over 2 minus 3 to the power 2 over 2. So that's 81 minus 9. And that's going to be 72 over 2, which is 36. So the definite integral is a number, and that's important to understand. Okay. What else? What else do I need to say here? Yes, the area under a curve. Area under a curve. Area under a curve. So if you have a function x and y, if you have some sort of function f of x, and this is point A, and this is point B, then the area under the curve is actually equal to the definite integral from A to B f of x dx. Right. We'll use that later on. Okay, moving on. Now, just a little bit of theory. Integrals containing ax plus b. So you know that the integral of x to the power n dx is x to the power n over n plus 1 over n plus 1 plus c. Wouldn't it be absolutely amazing if instead of x I had, for example, ax plus b to the power n? Wouldn't it be just really, really nice of calculus that this would be ax plus b to the power n plus 1 divided by n plus 1 plus c? And I have good news for you. It actually is, with one little tweak. You just need to put 1 over a in front. And that's it. So it works. So going from x, so replacing x with ax plus b, replacing x with ax plus b puts a 1 over a in front of the primitive. It's not a theorem. Now, if it were, well, it's not. It's not a theorem. Well, it's a rule. Okay, it's a rule you can use. I won't go too deep into explaining why. You can explore, and you should explore why it is so. But if you test this, if you take the derivative of this thing, you will get this, right? So I promise you that. So you can use using the chain rule. It does use the inverse of the chain rule sort of thing. You can show that using a substitution as well. But we don't do substitution in year 11, so I don't yeah, for now, believe me and explore on your own why it is so. And it works for other integrals too. So for example, if you have the integral of sine x dx is minus cos x plus c, then the integral of sine ax plus b dx is 1 over a minus 1 over a cos ax plus b plus c. And similarly for cosine x dx is sine x plus c. That means that cosine ax plus b dx is 1 over a sine ax plus b plus c. And straight away, we can do an example. It's an integral of 4 sine 3x. Integral of 4 sine 3x dx. 4 goes out, so that's 4 integral sine 3x dx. And we know that the only difference that it makes is there's a 1 over 3. So it's 4 thirds cosine minus 4/3 cosine 3x plus c. That's it. It's very straightforward. Okay. On a scale of 0 to 10, how well do you understand problem 2? Please, in the chat, on a scale of 0 to 10, how well do you understand problem 2? Okay. Is that a 0 or a 10? Okay. So the thing is, if you find the derivative of that, it's minus 4/3 cosine 3x plus c. If you were to take the derivative of that, it's going to be minus 4/3, and then use the chain rule here. It's going to be 3 minus 3 sine 3x. And if you simplify that, and plus 0, and if you simplify that, the 3 cancels, the minuses cancel, it's going to be 4 sine 3x. So you find a function whose derivative is 4 sine 3x. I'll do some more examples. This integral of sine x dx is minus cos x. We already know that. So the integral of sine 2x plus 3 dx is minus 1/2 cos 2x plus 3. The integral of sine 4 minus 5x dx is going to be minus 1 over minus 5 cos 4 minus 5x plus c, which can be simplified as 1/5 cos 4 minus 5x. Okay. Right, now moving on to the definite integral. And we apply the same rules here. First, we find the integral itself. And integral from 0 to pi over 4 cos 2x dx. So it's 1/2 because there's a 2, so 1/2, and sine 2x between limits 0 and pi over 4. And we substitute pi over 4 first, so it's 1/2 multiplied by sine 2 multiplied by pi over 4 minus 1/2 multiplied by sine 2 multiplied by 0, which is, well, 2 times pi over 4 is pi over 2. So it's 1/2 multiplied by sine pi over 2 minus 1/2 sine 0 is 0. Sine pi over 2 is 1, and therefore it's just 1/2. Ta-da, that's it. Moving on to the next question. Area between two curves. So you have the you have two curves, and you need to find the area between them. So you would normally start with a sketch. So y equals x squared. So that's a function like this. It is from 0 to 2. So 2, so that means that this is 4. And y equals 2x. Y equals 2x. Oh, well, that's a straight line. Okay, so that's y equals 2x and y equals x squared. Well, we'll start by finding, well, there are two ways of doing it. Okay. Um, X and Y. So we need to find this area. So we'll start by finding area under this curve. So orange area. Orange area. Orange area is the integral from 0 to 2 of x squared dx. And then that would be x cubed over 3, because the antiderivative, so x cubed over 3 using the formula, between limits 0 and 2. So we substitute 2, and that's 2 cubed over 3 minus 0 cubed over 3, which is 8 cubed, 8 thirds. And then we can find the triangle, this triangle. And triangle, well, it's half times base times height. And the base is so 1/2 multiplied the base is 2. Height is 4. And that is okay, yes, that's 8 halves. Or just 4. Okay, so that's 4. And so area between the curves, is 4 minus 8 thirds. It's just 12, so that's 4 thirds. Okay, lovely. The alternative way of doing it, well, you can say, well, if you have two curves like this, and you need to find the area in between. So this is f of x, and this is g of x, and then between points A and B, because you can see that f is above g, so you can find the integral of f of x minus g of x. So integral of the difference between them, dx. And that's what you can do here. So this is the integral of 2x minus x squared dx between limits 0 and 2. So you can substitute that. So it's the upper function, so upper minus the lower. So 2x is the higher, it goes above, and x squared is the one that goes below. So, okay. And then you just integrate that. And we know that the integral of 2x is x squared. So that's x squared minus x cubed over 3. And we substitute 0 to 2. And so that's going to be 4 minus 2 cubed over 3. So it's 4 minus 8 thirds, which is 4 thirds, which is exactly the same answer. So I hope that makes sense. Okay, so that's problem 1. Okay, that's 1A. 1A. That's 2, 3. That's problem 4. So the next is problem 5. Area between two trig curves. So we need find the area enclosed between sine x and cosine x. So if you draw them, and sine x is like this. So this is pi, this is sine x. And cosine x, that's here. Like this. This is cosine x. And well, pi over 4, well, that's this point, actually, where they intersect. This is pi over 4, because this is pi over 2. And so we need the 0 pi over, so we need this area. So this is cosine x, and this is sine x. So the area is going to be the integral of cosine x minus sine x, because the upper minus the lower dx, between limits 0 and pi over 4. And we just integrate. So very, very, very straightforward. So integral of cosine x is sine x, minus integral of sine x is minus cos, so plus cos x. And we substitute 0 and pi over 4. So substitute pi over 4 first. So that's going to be sine pi over 4 plus cos pi over 4 minus sine 0 plus cos 0. Okay, so sine pi over 4 is square root of 2 over 2 plus square root of 2 over 2 minus minus sine 0, minus 0, and minus 1. To square root of 2 over 2 plus square root of 2 over 2, that's square root of 2. That's square root of 2 minus 1. And that's the answer. That's the area. That's the area between the two curves. So I don't know if you see, but this is an incredibly powerful tool. You can find areas pretty much any area if you know the function. Okay, with few exceptions, right? So some graphs you cannot integrate, but that's yeah. Okay, now we get to the interesting part, and the part that is very rarely discussed in a school setting. Is called the Riemann sum. The Riemann sum. So this looks like this. Imagine we have a curve. In this case, it is x squared. X, y, x squared, and it looks something like this from 0 to 3, which is 9 here, of course. We want to find the area under this line. We want to find this area. Area, question mark. We already know that the area is this integral. Right, we've learned this. We haven't explained why, but okay. Now, let's split this this thing vertically into 3 columns. And as a height of the column, I'm going to take the left a right endpoint. Right endpoint. Okay. So this, I'm going to take this point. So this is 1, this is 2. And I'm going to okay. So I'm saying that the area of these 3 rectangles is slightly more than the area under the curve. Okay. So total area. So area of 3 rectangles. Well, this we know that this is 1. We know that this is 4, and that we know that this is 9. So it's 1 plus 4 plus 9, and that's 5 plus 9, that's 14. 14. We know that it is bigger. We know that it is more than the area under the curve because of these bits, these extra bits here. But what we do next is we reduce the width of the rectangle. Reduce the width of the rectangles to 0.5. And I'm going to, you know what? To be consistent, I'm going to redraw it. I'm going to copy it, I mean, for consistency. So I'm going to remove the unnecessary bits. Okay. So what I'm going to do is I'm going to split it now into 6 rectangles. 1.5, sorry, 0.5, 1.5, 2.5. And here I'm going to take this rectangle, this rectangle, this rectangle, this rectangle, this rectangle, and this rectangle. Okay. And then I can recalculate because now I know this is 0.25 because 0.5 squared is 0.25. 1 is 1. 1.5, that's 2.25. This is 4. This is 6.25. And this is 9. So that's going to be 0.5 times 0.25. So 0.125 plus or 0.5 plus 0. No, 1.125 plus 2 plus 3.125 plus 4.5. And if I add all of these together, so 0.125 plus 0.5 plus 1.125 plus 2 plus 3.125 plus 4.5, and that gives me 11.275, which is less than 14. But yeah, you can see this is still an overestimation. Now, I've overestimated the area by this amount, so that's an overestimation. So what I'm trying to do is I'm trying to find the area under the curve by finding the area of these rectangles, but the rectangles will always be slightly bigger than the area under the curve because of the way I've calculated the rectangles. Does that make sense? Do you understand what I'm trying to do? You could take the left and right Riemann sums and calculate the mean, absolutely, and that would give you an even better approximation, of course. Yes, but for now, I'm just doing the right Riemann sums, an overestimation. But you can see that the number will get smaller, and if I do half intervals, if I carry on doing it, Oh, that's annoying. If I carry on doing the same thing, I'll get closer and closer to the actual value. All right, so if I do 12 intervals now, you will see I get this, this. So as you can see, as I get as 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 n is the number of increases, is the area under the rectangles gets closer to area under the curve. Area under curve. Okay, so let's formalize. Let's do it properly. So consider. So imagine we've split into n rectangles. And imagine we've split it into n rectangles. Right. So pum 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 pum. And this is x. So n rectangles. We'll call this value xi. Consider rectangle number I. Now, I have to say, do not worry if you don't understand this. Okay, it will take approximately 6 or 7 times until you finally get it. If you're lucky enough to get it on the first attempt, well done. It took me a good 5 or 6 explanations before I understood what's going on. So please do not worry. This does sink in. It does. I did it the first time when I was in school and I was your age. Then I did it. Then I did it again in year 12 and again in year 13. And then I did it at university. And I think by the time I finished university, I actually understood it. I was like, oh, that's what it was. That's what it is. And you do this with a lot of things. A lot of things they just come to you. They sink in. You think about it. You think, and then it says, yes. Now I achieved the wisdom. So don't worry. So imagine a number I, the right edge. So the right rectangle number I, uh, the height of that rectangle is yi. The height of the rectangle is yi. The width is, well, it's 3 divided by n because there are n rectangles, so the width is 3 divided by n. Okay, so the area of that ith rectangle area is well, is yi, which is xi squared, is yi multiplied by the width, which is 3 over n, which is xi I squared multiplied by 3 over n. But what is xi? Well, xi is I is the number of the rectangle. So you make n steps. So it's 3 over n multiplied by I. So that's 3 over n multiplied by I squared multiplied by 3 over n. We can simplify that. That's 9, 27 over n cubed multiplied by I squared. Okay. And the total area, so that's the area of the ith rectangle. Area of ith rectangle. But there are n rectangles in total. So the total area is the sum of all the areas AI of AIs, which is the sum of 27 over n cubed multiplied by I squared, and I is from 1 to n. And 27 over n cubed, sum of I squared, where I changes from 1 to n. And this value, the sum of first n square numbers, has a value, sum of first n square numbers. There's a formula. I never remember it, but it's this. And so that's going to be 27 over n cubed multiplied by n plus 1 to n plus 1 over 6. Lovely. Okay, and that's the total area. So total area is, let's open the brackets. So 27 over 6n cubed multiplied by n 2n squared plus 3n plus 1. Open brackets, 27 over 6n cubed multiplied by 2n cubed plus 3n squared plus n. And 27 and 6 cancel. That's 2 and 9. So 9, open bracket, well, 18n cubed plus 27n squared plus 9n all over 2n cubed. And now I'm going to divide top and bottom by n cubed divided by n cubed. Well, okay, let's not go ahead of ourselves. So this is the sum. So for n rectangles, the total area is 18n cubed plus 27n squared plus 9n. Why am I copying that down? I don't know. Cubed. Right. What is the limit? Is the limit if the number of rectangles tends to infinity. So basically we make more and more rectangles. So the limit, so S infinity is the area, the infinity area. So limit as n tends to infinity of 18n cubed. Okay, unnecessary. Of that value. To find that value, I divide top and bottom by n cubed. You'll see in a minute why I'm doing this. It's the limit of n tends to infinity. I'm dividing top and bottom by n cubed, so that's going to be 18 plus 27 over n plus 9 over n squared divided by 2. So divide top and bottom by n cubed. But as n tends to infinity, 27 divided by infinity, that's 0. That tends to 0. And 9 divided by n, that's also tends to 0. So the limiting value is 18 plus 0 plus 0 divided by 2, which is 9. So the limit, as the number of rectangles tends to infinity, the area tends to 9. And so for the cherry on top, let's calculate, compare. The integral from 0 to 3 of x squared dx is x cubed over 3 between limits 3 and 0. And that's 3 cubed over 3 minus 0 cubed over 3, which is 27 over 3, which is 9. So, conclusion. The sum of the areas, the limit of the sum as n tends to infinity is equal to the integral of x squared, x squared dx, yes, 0 to 3. Okay. Now, let's visualize it a little bit more. Riemann sums simulation. Okay, so let's say x squared, left endpoint is 0, right endpoint is 3. So this is this is using left hand, right hand is 1. Okay. Okay, so you can see, and this n is the number of intervals. So for 3 intervals, it's like this. N is 4, 5, 6, 7, 8, 9, 10, 11, 12. And as you can see, as n increases, the green area becomes closer and closer to the area under the curve. So that's what we mean when we say that as n tends to infinity, this area becomes the area under the curve. And the integral approximation is 9. So for this situation, the integral is 9. And you can see that it is an over approximation. Whereas if I take the left end Riemann sum, so that's 0. This is an under approximation. And for n 100, this would be 8.86. So it's slightly less than 9. And if I go back, I can take the center. And now this is a better approximation. So look, even for n equals 13, it's always also really, really close. So here we take the height at the middle of the line rather than left edge or right edge. So they're all valid Riemann sums, but here we just do. How do you do this with 3D shapes? Okay, that's a good question. Can I just show you one more thing? A slightly different approach, because this approach is slightly confusing because it's too specific. So imagine you have a random curve, x and y, and you take and you split you split the from A to B, you split it into vertical strips. You take one such strip. So let's take this particular rectangle. if there are many rectangles, you can say that the width of this rectangle is dx. Dx is the width. And the height, well, it's just the y. It's the y value. And this is x. Well, this is x, the coordinate. Xi is the coordinate and yi is the height. So the area of this area, AI, the area of this strip, is yi multiplied by delta x. Okay. But the whole area is made of n such strips. So the total area is the sum of yi delta x. But area under the curve is approximately the same as this total area, yi delta x. But as n tends to infinity, the limit as n tends to infinity of this expression, yi delta x. I don't know if you can see it or not. Do you recognize it? But as n tends to infinity, this sum symbol becomes an integral. Yi simply becomes y. And delta x, because the number of strips becomes infinite, becomes dx. So you can see how this transforms into that. And this is absolutely fascinating. And it's very useful here. Because what you do is, because yi, we know yi is simply xi squared, and so the sum of, so the limit of n tends to infinity of xi squared delta x simply becomes the integral of x squared dx. And of course, we have the limits from a to b. So you see how this is interlinked. So when you have a 3D shape, like imagine you have a cone. A cone. Well, no, let's take a sphere. 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 And let's take a half sphere, semisphere. Semisphere, and this is x, this is y. Right. So a semisphere looks like this, of course. Right. So this is a semisphere. What I'm going to do is I'm going to cut the semisphere into slabs. So you're going to slice it. Cut and take a knife and just slice it like this. And I will end up with cylinders. I could think of it as a big cylinder, on top I have a slightly smaller cylinder, then a slightly smaller cylinder here, and a slightly smaller cylinder here, and a slightly smaller cylinder here. So these are made of cylinders. So I'm going to take this cylinder, and find its volume. So cylinder number I. So this cylinder number ith cylinder. This is delta x. The radius of the cylinder is yi, and y is the height, is this value, right? So this is that cylinder. So yi is the height, or well, in this case, it's the radius of the cylinder. So the volume is pi r squared, pi yi squared, multiplied by delta x. Okay. And then what else? What else do we need? Well, that's just a one cylinder. So the total volume is the sum of pi yi squared delta x, total volume of the cylinders, but the volume of volume of the sphere is we take infinitely many cylinders. So it's the limit, as n tends to infinity of this value, pi yi squared delta x. And that limit is in fact the integral from 0 to r, because that's the biggest value on x. So this is r, and this is r. And that curve y is equal to, because if you know the equation of a circle, x squared plus y squared equals r squared. That means y is square root of r squared minus x squared. So because y is square root of r squared minus x squared, I'm going to stick that in. That means y squared is just r squared minus x squared. It's going to be the integral from 0 to r of pi multiplied by r squared minus x squared square root squared dx. Like delta x becomes dx. And I remove the square root because there's a square, and pi goes out. So pi integral of r squared minus x squared dx. And I'm going to integrate that using the linearity of the integral. It's going to get pi. R squared is a constant, so it's just r squared x minus x cubed over 3 from 0 to r. Those are the limits. And if I do pi and I substitute r, so that's going to be open bracket r cubed minus r cubed over 3 minus just 0. So r squared r cubed minus r cubed over 3, that's 2r cubed over 3. So pi multiplied by 2r cubed over 3. And that's the volume of a semisphere. So semisphere is the volume is 2/3 pi r cubed. I hope you know where I'm going with this, because the volume of a sphere is simply 4/3 pi r cubed, because it's just double the volume of a semisphere. Does that answer your question, Ari? So you cut it into cylinders, not rectangles. Okay, and we use that a lot. We use that a lot in Compos. And once again, don't worry if you don't fully understand it. It really takes time to sink in. It's one of those things. And then this one, I love this because I was looking at questions for university interviews, and this is one of the questions. One of the questions from an Oxford interview. A point is chosen at random inside a unit square. What is the probability that the point is closer to the center of the square than to any of its edges? Okay, what does that even mean? So a unit square, let's say it's a square at 0, 1, and this is 1. Okay. And you choose a random point inside the square. What is the probability that is closer to the center? So this is the center. And to any of its edges? Well, you employ the law of symmetry here because you can split the rectangle like this. So sorry, split the square like this. And let's just find the picture here, because if we find the points which are equidistant, so obviously this point is here. So this point is equidistant from the line and from the center. That's fine. But what about here? Well, here we'll have something like this. So here the same distance. Here the distance is the same. This distance is the same. So we need to find all these points which are equidistant. Okay, so let's take P. P, X, Y is a random point. Random point inside the square. Distance to 0. O is the center. No, O is not the center. C is the center. C, 1/2, 1/2 is the center of circle. And yeah, so the distance PC is the distance from P to C is the square root of x minus 1/2 squared plus y minus 1/2 squared. That's the distance to the center. Center. The distance to line y, OY, the y-axis, is simply, well, just y. It's just y, because if the point is xy, then the vertical distance is just y. And this distance is, well, that, BC. Okay. And they have to be equal. We want to find where they are equal. And so that's square root of x minus 1/2 squared plus y minus 1/2 squared must equal to y. So square both sides, x squared, x minus 1. Oh, actually, we don't need that. X minus 1/2 squared plus y squared minus y plus 1/4 equals y squared. Y squared cancels, and we get y equals x minus 1/2 squared plus 1/4. Oh, lovely. It's a parabola. Parabola. It's a parabola. So we have it's like this. So we need to find this area and compare it to the area of the triangle. So shaded area is the area under the rectangle, under the curve. So we need to find these values of x. So this is 1. So we actually just need to find a half. Yeah, we don't need the whole thing. It's just 0.5. We need to find this area, and the area of this triangle, small triangle. Let's label them. This is A1. This is A2, and the whole thing is A3. A3. So to do this, we first find this point. This point. X is equal to y, because this line is y equals to x. So y equals to x, and y is equal to x minus 1/2 squared plus 1/4. And that is, substitute that in. So x is equal to x squared minus x plus 1/4 plus 1/4. X squared minus 2x plus 1/2 equals 0. going to be a bit lazy here. So 1 minus 2, 0.5, 2. So x is 2 minus root 2 over 2. In other words, it's 1 minus 1 over root 2. So that's the value 1 minus 1 over root 2 here. And then we find this triangle. So A1 is equal to 1/2 multiplied by 1 minus 1 over root 2 squared. That's the area of this triangle. A2 is the area under the curve. That's the integral from 1 minus 1 over root 2 to 1/2 of y, so of x squared minus x plus 1/2 dx. And if we substitute that in, so we just get, well, we get something. We get a number. So it's x cubed over 3 minus x squared over 2 plus 1/2 x. Oh, my computer's getting really hot. Okay, and then you substitute 1 minus 1 over root 2, 1/2. You know what? I'll just to save time, I'm just going to calculate it on. I'm just going to do it on my calculator. Would it be faster? Yeah, I think so. So it's going to be x squared minus x plus 0.5 between limits 1 minus 1 over root 2 and 0.5. And that's 0.054737. So that's a number. And A3 is the total area, and that is 0.5 multiplied by 0.5 multiplied by 0.5. So that's 0.125. And that's too small. X squared minus x. Have I messed something up? That's way too, oh, 54. No, that's not too small. Okay, that's fine. Yep. 0.0125, and that is 0.5 times 1 minus 1 over square root 2 is approximately 0.146447. And now finally the probability. So if you shoot randomly at a square, the probability that it's closer to the center. What did it say? Closer to the center. So closer to the center, there's going to be A3 minus A1 minus A2 divided by A3. And that's going to be 0.125 minus 0.146. That's not possible. Oh, squared. I've got to square it. Yes. 0.04289. 0.04289 minus 0.054737 all over 0.125, and that's the probability. Okay, and fraction 0.125 minus 0.04289 minus 0.054737 all over 0.125, and it's 0.22. So 22%. Pretty nice. Um, I hope you got something out of it. I know the last two questions were unreasonably difficult, but we do have questions like that in the assignment. Not the last one, but the one before with the Riemann sum. So do give it a go. Do try. Don't worry if you don't get it. It's absolutely fine. But yeah, try your best, and it's always about trying stuff you're unfamiliar with. It's always about trying to outdo yourself, if that makes sense. Okay. So yeah, hope this was insightful, useful, etc., etc. Hope you weren't bored today, and it was the last webinar of 2025. So the next one is going to be in January, and I believe it's yeah. So have lovely holidays, have a great new year, and I'll see you in January. Okay. Thank you.